cities are getting hotter every year, but how do we actually measure the urban heat island effect using satellite data? In this tutorial, I will show you how to calculate land surface temperature, analyze vegetation cooling, detect urban heat hotspots, and even build a regression model that predicts temperature across the city. And we'll do everything using Google Earth Engine and Landsat 8 data. So let's get started. Okay, so make sure you have your Google Earth Engine code editor up and running. So after you've opened your Google Earth Engine, the first thing is we need to load our dataset. So you go here to your search place and datasets on your Google Earth Engine code editor, and I'm going to paste in a code here, a collection. So it is just Landsat 8 collection 2 tier 1 level 2, and then you click on that. Then to copy the collection snippet, you can read through the description and also check through the bands. So these are the bands. You have the surface reflectance, band 1, surface reflectance, band 2 as blue here. You can see here we have blue surface reflectance, and we have band 1, which is the ultra blue or castor aerosol. We have band 3, which is green. Band 4 is red. We have band 5, this is the near infrared. We have band 6 here, which is the shortwave infrared. Band 7, shortwave infrared 2, surface reflectance. And then we have the QA aerosol. We have the bit mask. So this is the one you can use to remove the clouds. Then we have band 10, which is ST. This is the surface temperature processing level. And you can see that this is in Kelvin, which means this is the temperature. So we are going to use this to determine the land surface temperature and then perform a regression model. So after that, you can import these, or you can just copy the collection snippet as I normally do. So you come here and copy the collection snippet like that, then you just close. So here you need to say variable collection is equal to, then you paste the image collection, which is the Landsat 8, and then you can start to filter out the bounds or for the geometry. So you can filter out bounds. I've not created the bounds yet, so up here before this line, I would like to create the geometry or the region of interest. So I will say variable A or I. You can say A or I, or you can give it any name. So area of interest is going to be ee.geometry point. So I'm going to use the buffer method to get like a buffer of like 2 kilometers or whatever the distance you like to get. So here I'm going to say point, and then I'll pass in a list of coordinates here. So I'll pass in 36.8219. That is the latitude and the longitude, and then the latitude is going to be negative 1.2921. Then outside here I'll say dot buffer, and I'm going to buffer to a distance of let's say 25 kilometers. And then I'm going to center the object. So I'll say map.center object, map.center object. And this is going to be our AOI with a zoom level of around 10. Okay, so after I've done that, then down here, I'm going to now make sure that I filter out the bounds using the AOI that I've just created. So I'll say dot filter, and I'll filter out bounds, and then I'll say filter bounds. I pass in my area of interest, then I filter out the dates. So I'll say filter dates, and this one is going to be from 2023 January date 1st up to January up to December 2023. So I'll say 2023 December like that, and then 31st. Okay, then I'll also try to filter out some cloud cover. So here I will say dot filter. You can filter metadata, or you can use this advanced function. So you can say ee.filter dot less than, so you are going to filter the cloud cover, and this is going to be less than 10. So cloud cover less than 10%, then we get those regions. Okay, so after you've done this, you need to save your work. So I'll put a semicolon there, click on Control Save, and then you need to save your file. So here I will say urban heat island underscore regression, like that. Then click on OK, and this is going to save your script here. So instead of new, you will see that we have our script file. Okay, so let's proceed. Now down here, the next thing is that we need to get the cloud mask, and the cloud mask is it is going to help us like remove some of the clouds that might be still overlaying on our map. Yeah, so even after filtering by cloud percentage, some individual images may still contain cloud pixels, so we need to also do that. Clouds can distort spectral measures measurements, so we need to remove them. And to do this, we create a cloud masking function. This function uses the QA pixel band, which I did show you in the bands. This contains quality information about each pixel. So using a bitwise operation, we identify pixels that are flagged as clouds, and then we can remove them. So once the cloud mask is applied, we combine all the filtered images using a median composite, and then this produces a single image that represents typical conditions for the year. Then finally we shall do a clip. So to do that, here we can write oops, I need to delete this up to that point. So then I can give a comment here and say cloud mask. If you also want to write, you can do so. So make sure you follow along. Okay, so here I'm going to declare a variable and say variable. So we know I'm just declaring a function. So declare a function here, function mask L8, and this one is supposed to be a function like this. Then we need to get the QA pixel band to help us remove the cloud. So we say variable QA, you write QA is equal to the image. Remember, we have not passed in this image.select. Then we are going to select the QA underscore pixel. So this is the band that is found in your Landsat 8 collection 2. If you just click on this, go to bands, then scroll down here. We have the QA band. This is the aerosol. And then if we go down here, you can see the atmospheric. We have the ST. We have the ST, we have the STQA. So we have the QA here, and then we have other pixels. So we have this one here, pixel quality attributes generated from the CF mask algorithm. Then we have the QA pixel bit mask. So this one, you see 0 is fill, bit 1 is dilated cloud, 2 is cirrus, and so on and so forth. Then we also have the cloud cover. I don't know is it, but you can find it somewhere here in the bands. Okay, so after that, we need to now declare an image here, pass in the image argument, because we are going to use it here. Then after that, we need to say var mask. So we need to create the mask that we shall use to update the rest of the image collection. So this is going to be our QA dot bitwise and. So you say bitwise and like that. Then you pass in and say we have this value here, and this is equal to 0. You pass in 0. So after that, you need to return the image. So return the image dot update mask like that. Then you pass in your mask. Okay, so after you've done that, that's the function that we are going to use to map through the image collection so that we remove the rest of the clouds that might be still remaining in the image collection. So next is now to map through. So here we need to say var image. So we create a new image. Then we say the collection. We need to say collection and collection dot map the function, which is mask L8, like that. It's here. So mask L8 is there. Then you also say dot median, and then we also say dot clip. So we clip to our region of interest. Okay, so after you've done that, the next thing is now going to be to calculate the land surface temperature, but first we shall need to change the Kelvin value to the degrees Celsius. So now we calculate the land surface temperature, often abbreviated as LST. So as you will see in the, or as you saw here in the image collection. So in Landsat 8, thermal information is stored in the AST band 10. So that is what we are going to use here. However, the values in this band are stored using scale factor. And so we must convert them to real temperature values. So first we multiply by the scale factor, and then we shall do the add the required offset. To see all these properties, you just need to go to your Landsat 8 here, go to bands, and then under band 10 here, where is it? Pixel mask. So we need to scroll up to band 10. So this is SR band 5. Band 10 is here. So if you just scroll towards the end, you can see here that we have the scale factor, this column. So the units, we have the scale here. If you scroll down, you see the scale. So I'll need to change this to light theme. I'll need to see everything first. So here in your, I'm sure you don't have this, but I would like to change to remove dark theme. Yes, very nice. So here you can see this column is the scale factor here. So this one, and then the other one is the offset. So we are going to multiply by the scale factor, and then we add the required offset, and then finally we convert the temperature from Kelvin to degrees Celsius, and the result is our land surface temperature layer. That represents how hot different surfaces are across whatever the region of interest you are using. Okay, so for that case, I'll just go back to my dark theme. So I will scroll down here, change this to my dark theme like this. Then I close the image collection. Okay, so you can leave a comment here and say LST or land surface temperature, and then you can say this is in degrees Celsius, like that, Celsius. Okay, so you need to declare a variable down here. So go to the next line and declare a variable. Say variable LST is equal to the image that now we have above here. So this is a cleaned image. We don't have like clouds here because we have mapped through the function that we did use to remove the clouds in the image. So now this is like our image collection now. Then you say image. So LST is equal to image dot select. We are going to select the ST. So you say ST underscore band 10, like that. That's as it was in the image collection. Then you come here to a new line and they say dot multiply. So we are going to multiply by the scale factor and add the required. So these are just numbers, random numbers that you can choose in between whatever the range that we saw in the image collection. So we are going to multiply this by, so say multiply, we are going to multiply by the scale factor, which is 0.00341,802, like that. And then we say dot add. So we're going to add 149.0. Then to convert to degrees Celsius, we need to subtract from 273. So we say dot subtract dot subtract, and we are going to subtract from 273.15, and then we need to rename these. We need to rename these to as LST band. Okay, so click on save, and so we have our LST image. Okay, so we move on to also calculate the NDVI. So we compute the NDVI, which is the normalized difference vegetation index. And NDVI is one of the most widely used indices in remote sensing because it measures vegetation health and density. It is calculated using two spectral bands, that is the near infrared band and the red infrared band. So if you just go back to your image here, image collection, go to the bands, and you see that we need the near infrared band, which is band 5, the near infrared here, and we need the band 4, which is the red band. Okay, so that's how we calculate the NDVI. So down here, calculate NDVI. So you can say calculate NDVI like that, and then you can say var NDVI. So you just give it an variable NDVI is equal to, here we need to get the image still, so image dot normalized difference. This is a function from Google Earth Engine to calculate the normalized difference. So here you say you need to get band 4 and band 5. So band 4 is the near infrared, and band 5 is the near infrared, and band 4 is the red. So you say band 5, so SR underscore B5, and the next one is band 4, which is SR underscore band 4, like that. Then we are going to rename this. So we are going to rename this. You can write it here if you like. Rename this to NDVI. Okay, so the next thing also, we need to calculate the built-up index. So to calculate the built-up index, we shall use the short wave infrared band and the near infrared. So that is band 6 and band 5. So while NDVI highlights vegetation, NDBI, which is the built-up index, highlights urban infrastructure. So the things like concrete, the buildings, the roads, and all those things, like, and other urban surfaces that you may think of apart from the vegetation. Okay, so by mapping NDBI, we can identify areas with dense urban development, and then for the NDVI, of course, it is for vegetation index. Okay, so you can also write here comment and say you can say NDBI index, NDBI index, like that, or this is like the built up. So you can also even say here that this is vegetation, this is vegetation index, and then down here this is the built up index. So you can say built up index. Okay, then you can also do the same thing. Variable NDBI is equal to the image dot normalized difference. You pass in the bands as we've said. So we need band 6 and band 5, the shortwave infrared and the near infrared. So you can say SR underscore band 6, and then band 5, which is SR underscore band 5, like so. Then you can also do the renaming thing. So you can say rename this band to NDBI, like that. Okay, so the following thing is we need to get the visualization parameters so that we can visualize these two layers, the NDVI, the LST, and also the NDBI. So for temperature, we can use a color palette that transitions from something like blue to cooler areas, of red for hotter areas. Then for NDVI, you can use ranging from maybe brown to green, which will help us like represent the representation of vegetation density. Then for NDBI, we can use some shades of gray and black. Okay, Then I think after that we shall just need to add them to our map so that we can visualize them here actually, because we have not yet run our map. So here you can write a comment and say visualization params or parameters if you like. Then here you need just to say create a variable for LSTVs. So LST visualization is equal to an object that has the minimum value of 20, and then the maximum value of 40, and then the palette, you can provide the palette here. And the palette, of course, is a list of colors, so we need to get the blue color. The second one is the cyan. Then the next one is green. Then the next one is yellow like that, and the last one is red. Okay, so you can just copy this variable, and then you can use it several times. I'm going to duplicate 2 times and then change here the comment to NDVI. So I can say NDVI visualization parameters, and down here you can say you can say NDBI visualization params, like so. So for NDVI here you need to change this to NDVI. So NDVI visualization parameters, we are going to come from -0.5. You can begin from whatever the point you like, -0.5 to 1 to 1. And then the color palette, we need brown here, so we type in brown. We also need so brown color like that. We need yellow and green, so I'm going to delete cyan here. I'm going to also delete the red color. I'm going to cut this green color and put it at the end like that. So we have brown, yellow and green for NDVI. Then for NDBI here, we also need to change to NDBI visualization parameters. This is going to come from -0.5, -0.5 to something like 0.5 like that. And then I'm going to change the colors. So here I would like to have white color. Then here I would like to get gray, and then lastly I will have to have black, like so. Then I'm going to delete the rest of the colors. So this way you have the visualization parameters for all our images, and so we can go ahead and perhaps add them to the map. So let's add them to the map. Okay, so here first I'll need to say Control S and then add them to the map. Okay, so here I need to create a comment here. So just say add maps to the layers, like so. And then here you need to say map.add layer. These are functions from Google Earth Engine, so add layer. And here we need to add LST. Then we pass in the visualization parameters, that is LST Vs, like that. So we already have it above. And then you just name your layer as land surface temperature, land surface temperature. You can duplicate this, so I duplicate this 2 times and then change from LST to NDVI. How did we name this? So we have NDVI, NDBI. Okay, so here you just need to say NDVI and change the visualization to NDVI, and then you change also the name here to NDVI, like so. Then also here we need to change to NDBI, then change the visualization parameter to NDBI, then you also change the name of the layer to NDBI. Okay, so control save that one, and then you need to run. So if you like, you can also add some more meaningful comment here or name and say this is vegetation, just as we did above, vegetation, and this is the built up. So you can say built up. So control save. Make sure you put semicolons here so that Google Earth Engine does not complain so much. Control save, then run the code. So let's see if we have done everything right. So here it says that cannot read property of LT here, cannot read properties of this. So let's see what could be the issue. I think we need to say ee.filter is supposed to be in caps like that. Control save, then try to run again and see if there could be any issue. Yep, so we don't have any errors here. That means everything is running okay. So you can see that we have added our images to the map. So we have the NDVI, NDBI, and land surface temperature. So this is our land surface temperature. And then you can just uncheck and check the NDBI for the built-up. You can also check the NDVI like that. So the next thing is that we need to get the regression model, sample out some of the pixels, and then get the regression for prediction. But before that, you can see here that for the land surface temperature, the red represents the areas with higher temperatures on the surface, and the greener, that means maybe there is large vegetation. They are low temperatures from the surface. Okay, so now down here we need to create a new comment down there. So we need to say that sample pixels for analysis. So as we prepare the data for statistical analysis, we need to combine the three layers, that is LST, NDVI, and NDBI, into a single multi-band image. Then we randomly sample 5,000 points, pixels. So you can choose the number of pixels that you like to get. So you remember that when you get to sample a very high number or a very large number of pixels, the lower the model will take. The model will take longer time to process. So that means that the process will become slower. Then each sample pixel contains like three values. So we shall have land surface temperature, the NDVI, and the NDBI. Then these sample values will allow us to analyze the statistical relationships between temperature, vegetation, and urban development. So I hope you get the point. So we need to say sample pixels. So pixels are just like we are going to sample out points for analysis. You remember when you are doing like in ArcMap, when you want to perform land surface, not land surface, but land use land cover, you need to get the points for each of them, like the class you have created. So if you have like 5 classes, let's say built up, water, you have built up, water, vegetation, you have grassland, and all those classes that you've created. You go to the tools, and then you start selecting the points from the Landsat image or whatever the image that you are using. So you get those points, and then you run them through a model, whether is regression model or random forest, and so on, so that you get the image, the predicted values for the image. So that's the same thing that we are going to do here. So we like to predict the land surface temperature on our region of study. So here I'll just say for analysis, like that. So down here, first you need to say variable combined. So just say combined is equal to the LST. As we have said, we are going to combine those. So we add bands together, add bands, and then we add NDVI. Then we say dot add, also add NDBI. Okay, so after we've done that, the next thing is now to sample out the points. So down here you say variable samples is equal to combined, so the combined image here, or the bands, dot sample. So we use the sample method from Google Engine, sample, and then we pass in the parameters that we like to get. So first, of course, we need to sample here on the region of interest. So region is going to be our AOI, and then we also need to get the scale. So the scale obviously is going to be 30 pixels, resolution, then the number of pixels, so this is what I was explaining, number of pixels. You can choose 10,000, 20,000, 100,000. I'm just going to use 5,000, so 5,000 like that. And then the geometries, I would like to ignore the geometries for now, so I'll say false. So geometries is equal to false. And then so after that, we need now to like create a scatter plot for NDVI and LST, and we create another one for LST and NDBI. So the first scatter plot explores the relationship between vegetation and temperature. Each point, of course, on the chart will represent like one sampled pixel. So first, let's create those so that when I'm explaining, you will get to know exactly what I'll be doing. So down here, you need to also have a comment, perhaps you like to, and then say just create a scatter plot, and a scatter plot for all those charts that you like to get. So here we are just going to create a chart. So variable chart, chart for NDVI, chart NDVI is equal to the UI.chart feature by feature like that, and then we pass in the samples. So our samples like that. Then we say NDVI, and then we also say LST. So get the samples for NDVI and LST. Then after that, we need to say dot set chart type. So set chart type, and the chart type is going to be our scatter plot, scatter chart. So make sure you type out correctly, because this one is a scatter chart, which is like a keyword here in Google Engine. And then we need to set options. So you say dot set options. So these are options for our chart. So remember, a chart has a title, vertical axis, horizontal axis, and all those things that you like to have in your chart. So the first one is the title, and the title is going to be LST versus NDVI, which is our vegetation index. So here you can type in vegetation index. Okay, that is the first thing or property. Then we also need to get the horizontal axis. Horizontal axis is the x-axis, and the x-axis is going also to have a title. So we need to get the title here, and the title is going to be NDVI. So we do vertical axis here, so v-axis, and this is going to also have a title. The v-axis is going to have a title here, so type title, and the title is going to be LST in degrees Celsius, like this, degrees Celsius, like so. And then the next property is the point size. So down here you need to say point size like that. And the point size could be any size that you like. If you want them bigger, then you can do something like 5, 10, and then I'm just going to use 3 here. So point size is 3, and then you also need to have the series. The series, you need to get the first one. For the first index, we need to get the color. So we need to get the color for our plot of our point, and the color here is going to be green. So I would like to have green color. If you leave it by default, it will be blue. So I have green color, and then the next one is the trend line. So I like to distinguish the points with the trend line. So I've said trend lines, and trend lines going to be also for the first one, we need to have the color, and the color is going to be red. So I like to get it by red color. And so after that, you also need to pass in some other properties. We need to show the r squared, show r squared is going to be true. So I'll explain this one later. And then you also need to have the legend visible. So we say visible legend. This is like a Boolean value. Legend visible in legend is equal to true. Okay, so after that, we need to now print the chart. Okay, so down here you need to say print chart, print NDVI chart. So chart NDVI, print chart NDVI. Okay, so put a semicolon at the end, and then just save, click on save and run. So I will enlarge this and just show you how the chart looks like. Yeah, so you can see here that we have the chart, which is the LST versus NDVI, which is the vegetation index. We have the legend here that shows the points at LST and LST. We have the trend line there, and then you can see. So you can open this in a new. Tab. So click on that icon. This one is going to open in a new tab here. So you can see that what this graph shows that it shows a negative relationship, meaning that as vegetation increases, the temperature tends to decrease. So here you can see we are coming from -2 here to around 0.6, which is so 0.6 means that we have higher vegetation index. And then when it is 0.2 negative, that means that we have low. So for example, when the vegetation is low, very low, then the temperatures are very high. Then when the line tends towards 1, that means that the vegetation is increasing, the temperatures tends to reduce. For example, here we have 25 degrees Celsius, and we have the LST, we have the NDVI as 0.428. So the first value is for the NDVI, and the second value is for our land surface temperature. Yes, so we also need to create the chart for the NDBI, and you will see the contrast between the two, and that one will help us actually understand that that relationship between NDVI built-up index and also the land surface temperature. So let's do that just here. So down here, I'm just going to copy this code for the chart for the NDVI. I'm going to copy this one up to here. So I copy that, and then I can write a comment down here and say that this is for the NDBI scatter plot, like so. Then I'm going to paste it here. So let me just reduce this one. We are going to change the NDVI to NDBI, also change the samples here to NDBI versus LST. Then the scatter plot obviously is going to remain the same. We change the title to NDBI, which is here we need to say built up. So you say built-up, so built up index. And then the title also will change to NDBI. The degree Celsius, of course, will remain. Then the color, we can choose to use a different color here for NDBI. So we can use black here, say black, supposed to be lowercase, black. And then the color for the trend line, we can choose to use a red color for still to be the same color. Okay, so here we have our NDBI. So let's print and see if it actually prints out the chart. So make sure you change the print name value here to NDBI. So control save and then click on run. So we need to see both the charts here, and then you will see the contrast between the two. Okay, now you can see that we have two scatter plots. The first one is for the vegetation index with versus LST, and then we also have the NDBI, which is a built-up index versus LST. You can see the difference between these two graphs. So the first one, when temperature decreases, the NDVI tends to increase. But for the built-up, you can see that it is kind of directly proportional. When we have more urban infrastructure, then we have higher temperatures. Okay, so here you can see that the line typically slopes upwards than the one for the NDVI, which slopes downwards. This produces a negative slope, but this one produces like a positive slope. Okay, so as I've said, trend line here slopes around upwards. This means that the areas with more urban infrastructure then have higher temperatures, just as you can see here. So when the NDBI is around 0.15 as the index, the temperature is like 43 and above degrees Celsius. Okay, so this is how we get to analyze these two parameters, the NDVI and the NDVI, and also the land surface temperature. So I hope you have gotten something there. So we move on to perform the multi-regression analysis, which we are going to do next. Okay, multi-regression analysis means that instead of predicting temperature using a single variable, we use two predictors. So we can use NDVI representing vegetation and also NDBI representing built-up areas or built-up surfaces. So to calculate this, we need to have some coefficients for both NDVI and NDBI so that we can multiply by each of these, and then we get the temperature, that is the LST. So temperature will be the coefficients multiplied by both NDVI and NDBI. And then this model will allow us to estimate how both vegetation and urban development influence temperature simultaneously. Then later on, we can create a predicted temperature map, and then we add it to the map. So to do that, we just need to have to create a regression model that will help us do the predictions. So here you can have a comment and say multilinear regression, and then as I've said that to get this temperature, we need to get the coefficient. So we can have a coefficient like A, then we multiply by the NDVI, and then after that we also need to get another coefficient like B, then we multiply by the NDBI, and then we can add the intercept like C. So there could be any other value where the line is actually cutting through the y-axis, or when the line meets the y-axis. So this is just the most basic formula that I can write here, but we shall see that. Anyway, so we need to create a variable here and say regression is equal to the samples that we got above dot reduce columns like this, and then we pass in some of the parameters that we like to use. Since we are using reduce columns, we need to use reducer, and the reducer obviously takes an EE.reducer method from the Google engine. Then we call the linear regression model here linear regression, and of course the linear regression is going to have some num x, just a number like x. So we need to have x like x there. We need to have x as 2. Then you can also have a num y. So this is a random number here like num y, which is 1. So after that we need to have selectors. So the selectors, of course, is going to be NDBI, NDVI, and LST, because we are using regression analysis. We are supposed to combine all the three like parameters or selectors that we have created. So down here inside the regression, the reducer method, inside the reduce columns method, we need to have the selectors. So you type in selectors, and the selectors is going to be a list of NDVI, that is NDVI. Of course, we have the NDBI, and then we also need the LST, so the land surface temperature. And then after this, we need to so after this, we need to print. We can print out the regression model and see what we actually get. I'm getting an error here. This says that expected to match with this on line 107. So we have this one here that closes there. Okay, so here we are supposed to remove this. We need to use a comma there because it's like kind of a list of properties inside the reduce columns. So down here we just need to say print, supposed to be lowercase, so print out regression, multi-regression. So you can say multiple regression, and then we can pass our regression here, regression. Okay, so confirm the spelling. You can save and then run the code. So down here you can see that we have multiple regression, and we have the values for the coefficients. So we have the coefficients for that one, and we also have the residuals. Okay, so we are going to use these coefficients to get to have an array, and then multiply by the NDVI coefficient, get those coefficients, and then use them to predict for our land surface temperature for both NDVI coefficients, and also we add them to the map. Okay, so here we just need to have let me put a semicolon here. So down here you can just say we are going to create, of course, the coefficients, which will help us to extract the regression. Of course, we are going to create coefficients that we'll use to extract the regression. Okay, so down here you just say extract regression, coefficients like so. Then down here you need to create a variable and say coefficients, variable coefficients is equal to the ee.array and array of regression, and then we need to say .get. So we are going to get the coefficients like so coefficients. Okay, so that way you have our coefficients. Then we need to get coefficients for NDBI and NDVI. So variable NDVI coefficients is equal to the coefficients. So this variable here, we paste it there, and then we say .get coefficients. So we get the coefficients, and this is going to be 0, 0, 0, and then we can duplicate this for NDBI. So change this one to NDBI, and then of course we shall get this from 1 and 0. Okay, so if we do that, put a semicolon here. So there we can print both the coefficients. So you can say print, and then you can say NDVI coefficients, and this is going to be the NDVI coefficient. Duplicate this, and then say this is the NDBI coefficients. So you change this one there. Okay, so after you have this, you can save and run the code. Okay, so here we have the we have the coefficients for the NDVI, we have 209, and then for the NDBI is 231. Okay, so we're going to use these regression coefficients to predict the temperature for multiple regression. So this is not going to be like a single variable here, that's NDVI and NDBI, but we're going to combine them and get the prediction for the land surface temperature. Okay, so here we need to continue and say predicted temperature map. So here we are going to say variable predicted LST is going to be supposed to be equals to the NDVI. So we have our NDVI. Remember our NDVI from above. So NDVI dot multiply by the coefficient, that is NDVI coefficient. So this is just like the formula we have here. So we need the coefficient we multiply by NDBI, then we add the coefficient that is multiplied by the NDVI, and then we can add an intercept. This is y-intercept. So coefficient there, then we can say dot add, because we are adding the NDBI, and this NDBI is multiplied by, so dot multiply, we are multiplying by the NDBI coefficient. Okay, so then we can say dot rename this. We need to rename, oops, let me do this. So here we say dot rename, and you're going to rename this as predicted underscore LST, predicted LST, like that. So after that, we need to get the variables, because we want to plot this on the map. So we want to get the variables. So once we have the regression model is computed, which we have already done, we extract the coefficients, which we have done for NDVI and NDBI. These coefficients, we can use them to apply the regression equation, so that we get the predicted temperature map. Okay, so down here we say that we get the visualization parameters. So regression visualization parameters is equal to, can get the minimum value as 20, that's as we had, and then the max value as 40. Okay, and then we can also have the palette. We can have the palette, have the color palette, and this is a list of colors. Obvious, we have blue, which will show the kind of flow temperatures, cyan, we have green, we have yellow, we have orange, and then finally we can have red. So red will mean that we have very, very high temperatures, predicted temperatures maybe in future. Okay, so after this, we just need to add to the map. So you say map dot add layer, map dot add layer, and then we say predicted LST. This one here, this is an image, so we say predicted LST. Then we pass also in the regression visualization, and then we need to rename this as predicted LST, which is through regression. Okay, so make sure you do this, and then if you run, I'll need to get this correct. So I'll enlarge this one here, control save, and then click on run. So expect to see the image here on the map. Okay, so here you can see that we have the predicted land surface temperature, and as you can see that this produces a predicted temperature map, which is which estimates temperature based solely on the combination of vegetation and built up surfaces. So you can see here the red ones have very high temperatures. This is just a predicted, surface. So it doesn't mean that this will be true, because of course at the central business district here, you are supposed to see very kind of large red, because that is where we have the built up areas. Okay, so after that we need now to do the residual heat map also, and this layer is created by subtracting the predicted temperature from the actual observed temperature. So in other words, it means that residual equals the actual temperature, then we minus the predicted temperature. So the map will highlight the areas where temperatures are higher or lower than expected. I think that is what the residual means. So we shall have the colors, and I will explain the colors as we move on. So here you just need to create the residuals. So I'll say residuals, residual heat map. And down here we can just create the residual. So variable residuals is equal to the LST dot subtract. So we need to subtract the real LST, so the actual, subtract subtract, we need to subtract the predicted LST, this one here. Then we can rename this to, so we need to rename, just say rename, and you're going to rename this to residuals like that. And then down here we can also create the visualization parameters. So var residual vis is equal to, we need to have the minimum value, we can choose 5. The maximum value is 5. Oh, it's supposed to be -5. This is -5, and then maximum is 5, like this way. And then we can have the palette, a list of colors, and so we need to get blue. We have blue color, we have white color, and we also have red. So of course blue areas are cooler than expected. That is what this one will mean. Then the white areas will match the prediction, so it will be like a medium value for the predicted. So if you plot on a graph, we are supposed to get that when we have normal temperatures, for the residuals, the white color should be at the normal, should represent the normal temperatures. Then red areas will be hotter than expected. Okay, so the red zones, of course, often indicate strong urban heat island locations caused by the dense infrastructure. So let's just plot that on the map. So down here, I will say map.add layer. We are going to add residual, and of course we pass in the visualization parameters like that, and then we rename our layer to residual heat map. Like that. So if you save your work, so click on save and then run this code here. If you run the code, we are supposed to see images. So we need to also have the residual heat map. So I'll remove those. Now you can see the residual heat map. As I've said, that blue areas are cooler than expected. So this one is cooler than expected. And then the white ones will represent, it will match the predicted value. And then the red zones are hotter than expected. So this is what we have as our residuals. So obviously the red zones often, as I've said, will represent the strong urban heat here. So if I just try to change this to satellite and check this, you can see that here at the CBD is where we have larger infrastructure, like buildings, all those roads. That's why we have a predicted value to be quite red. Okay, so this is it. We have learned a lot from this. We have performed land surface temperature, we have done vegetation and built up indices. We have also done statistical relationships between the two variables. We have done regression, prediction model. We have also done residual heat map. So all of these, of course, we have managed these through Google Earth Engine with the satellite imagery from Landsat 8. So these techniques are widely used in urban planning, environmental monitoring, and climate studies. So you can also try to do research and read some of the papers and see how you can also perform other predictions using maybe different prediction models. Anyway, if you found this tutorial useful, don't forget to like the video and also subscribe to the channel for more tutorials on GIS development, remote sensing, and also web mapping. So thank you for watching, and I will see you in the next video.